So, good morning, Professor Sumi Chen, and good morning, boys and girls. Yeah, I believe 9:30 is still quite early for these students. Yeah, but we just start. We can't wait all the students in the class. So today is another part of introduction of biosystem engineering. I'm going to present from the perspective of mechatronics. So provide all of you some basic knowledge in case when you are looking for the paper you are going to present, or you listen to the presentation given by other students. If they're talking about mechatronics, probably if you are not in this field, you may have the basic understanding, some elements they are talking about. So today I'm focused on mechatronics. So what is mechatronics? The word mechatronics was coined by a Japanese engineer from the company called Yaskawa. He's a motor manufacturer, very famous. And right now they also have made a lot of industrial robots called Motorman. So the engineer called Tetsuro Mori, he give the words mechatronics. Before that, there was another word called electromechanical. So you can see mechanical, electromechanical is combination of electronic system and the mechanical system. But this engineer put the mech in front of electronics. So emphasize that, especially from the motor point of view. We wanted to make a motor to rotate, to perform as desired as we want. So they put mechanical engineering in front of electrical engineering to emphasize that the main object is the mechanical role. And the electronics or electrical engineering is supporting that to make this mechanical system work as desired as we want. I think that belief, that's why he changed the order of from electrical mechanic to mechatronics. Okay. And in order to make these two terms work properly, we need another technology, software, to combine these two systems together. So bring together the area technology involving like sensor, the actuator, and also the microprocessor together, and work together and to analyze the behavior of the system, the mechanical and the electrical system, the behavior of that. And not only that, not only the analyze, but also to control the behavior of the system to meet our requirements. So that's the idea of mechatronics. So if you look at the figure here, this is the mechatronics. It involves the mechanical system and electronic system. And you are going to use the computer, computing power, computing technology to control the system. Okay, so this is the main idea of the mechatronics. And this can apply to automotive sector, aerospace, medical, railroads, and defense system, consumer product, manufacturing, and material processing. So we can use mechatronic technology to apply in this area. Mechatronics. I think in these days, we have to also include agriculture as well. I just give you an example of a mechatronic system. So this is the vehicle. And if you want to control the speed of the vehicle, so this is many, you can look at this, the object is a mechanical system, but involve a lot of electronics and also the computer inside the vehicle. We want to control the speed of the vehicle. We need a sensor. And we also need to compute the error between the desired speed and the actual speed. Compute and to output the control signal to the actuators. And so that the vehicle can perform the desired behavior we wanted to. So this is a mechatronic system, example of that. Okay. If we look at more detail, so this is the vehicle, right? And when you move, the speed will be censored by a sensor, will be measured by the sensor. So the speed will send to the computer for computation. And then the signal was sent to the throat for the engine to accelerate or decelerate, so that the speed of the vehicle will follow the speed we set for the vehicle, for example. That. Okay. So this is kind of the workflow for a mechatronic system. Okay. And in this structure, we call a feedback. The feedback. The term of the feedback is that because the speed of the vehicle will be measured and sent to the computer so that we know what's going on for the vehicle. This is the sense of the feedback, the core idea of the feedback. The speed will be measured and also monitored by the computer so that we can take some actions. Okay. In this structure, the feedback structure, the accurate speed can be achieved. Not only in an ideal case, even under different parallel of the vehicle. For example, if the vehicle is uphill or the downhill, the gravity will automatically change the speed of the vehicle, right? But because there's a feedback, there's a sensor, there's a computer, so that we can adjust the throat of the engine in order to maintain the constant speed. Okay, so that's the concept of that. Even under different parallel of the vehicle, we still can accurate speed tracking. Okay, that's one thing. So using the feedback, you can have two properties. One is we call it robustness to uncertainty. No matter you have many people in the vehicle, you're uphill, downhill, all kind of uncertainty, you still can maintain a constant speed for the vehicle. This is the concept of robustness. Okay. Another thing is we can use the feedback for design the dynamics. That means we can use the control technology to change the dynamics of the vehicle. For example, if the system, the response time is too slow, you are not satisfied the moving speed, you can use the feedback to accelerate. We call it change the rising time of the response. This is when you look at some machine, they are moving very slow. But if you put some sensor and the motor, and you can use the control technology to increase the positioning performance of the machine. That's what we call the design of the dynamics. So dynamics related to the response time. And here we can look at, for example, there are different response time. To change the response time from the very slow to very fast. We also can improve the accuracy of the positioning. Some system is not so accurate. They change the payload, the accuracy will lose. But with the feedback technology, you can change the dynamics so that even under different payload, you still can maintain the accuracy. So the dynamics performance will improve. And also the overshoot here, some system, for example, for the what can I say, luxury car, like BMW, they have some actuators on their damping system. So in different condition of road, they can change the damping vectors so that the acceleration after the bump will be very, very comfortable to the human. That's also, you can see here, that we call the overshoot. So with a feedback system, you can change the response time, you can change the accuracy, you also can change what we call the overshoot, the vibration acceleration behavior, so that you can use that to design the dynamics of this object. So that's some idea for a Mechatronics system. So we look at this Mechatronics system. Two sides, okay. So we have the control object, for example, the vehicle. And there's a terminology we call the plant. Okay. And then we assign a desired output command to the plant. Say, this is our desire, our command. Then we measure the actual output of the control object. So we have the sensors, and then we have the computers to compute the control signals, and we send the computer signal to the actuators. So this is the 5 elements for a Mechatronics system. Okay. If I speak too fast, please let me know. Okay. And in the later on, we are going to introduce in more detail on these elements. Okay. So we look at a Mechatronics system from a block diagram again. So a control system, a Mechatronics system, we have a control object we call plants, right? And then the actual output will be measured by a sensor. And the signal acquired by a sensor may be very noisy, have some noise to the measure signal. So we need some signal processors. It's called signal conditioners to fill out the noise and send to a controller to decide the behavior. The controller signals say we are going to accelerate or decelerate the vehicle, for example, and the actual signal sent to the the actuators. Okay. So the left-hand side in green color, this is implemented in cyberspace. For example, in the computer. So if you implement a control system, you're going to have a computing units here in the left-hand side. And this is the program you probably have to code in your computers. And on right-hand side in blue color is the physical space. So you have to, for a plant, you have to choose a right actuators. For example, you want to, it's an electrical vehicle, you need to choose the right motor for the wheel. Different actuators will have different dynamics. So you have to choose the right actuators. Also, you have to choose the right sensors so that the output will perform better related to the reference commands. Okay, so that's the control system in reality. As you remember, we need to analyze the behavior of the system. So you have to transform a control system in reality into a model. Okay, in transfer function. So again, this mechatronic system will be looked at again, but in mathematics, in transfer function. So we have to have a transfer function to represent the dynamics of a plant, the sensor, and also you have to think about what kind of transfer function here for the controller, so that the overall dynamics will meet your specifications, such as response time, accuracy, and overshoot. So this is also one of the important in the procedures when you are designing a mechatronic system. Okay. So these days, the autonomous vehicle is more complicated. What we just talked is here in the right down corner here. So you have a vehicle, right? You have the sensor, and then this is the command, and this is the actuators. So this is the mechatronic system we just introduced. But we call this is called we call a low layer related to the mechanical system, the servo layer. For an autonomous vehicle, you have called a high layer control. Here, for example, for an autonomous vehicle, you need some sensors, terrain sensors like the camera or the laser rangefinders, using the technology called STEM to build the map when you are moving. Right? This is the map. And then you have the map, you also have to localize yourself in the map. So you have to localization, and you have the map. Then you can build a course map depending on your desires. You want to move from location A to B in shortest time. So you are going to create a map which is related to the time. You want to find a shortest path to reach the goal. Or you want to save your gasoline. So the cost map will different depending on your desired your goal. And then you have the map, then you can use any searching algorithms to find a path from A to B through the different routes to reach the goal. Okay, and there are many algorithms for the path planning. Then you have the path planning. Then you generate we call the desired commands for the velocity, for the position, for the velocity or acceleration. Okay, and then send to the control system we just introduced in previous slides. Okay. So here you can see the feedback system is more complicated. They have to do. You have the sensors here. You have the sensor here. The sensor from the terrain sensors, they have some signal processing. We call the data fusion, sensor fusion. Okay. To build a map, to localize yourself. Okay. And then, the optimization for the path planner here, define then also calculate the trajectory for the vehicle. Okay. And here, we also have another called supervisory control. What that means? It's a human-machine interface. This is an autonomous vehicle. There's no human being inside the vehicle. For the traditional vehicle, you have a human drive the car. So, for example, if the wheel, the tire is flat, and then you stop your car, and then go down and fix the tires. But this is autonomous vehicle. So if the tire is flat and you don't aware of the failure, you still driving your car, it's going to be catastrophe, maybe, I don't know. So you need some high level, you can say the algorithms to deal with like a sensor actuator failure or anything. It's called supervisory control. If it's a fatal error, then you have to stop the car and send the signal to the base for some backup reaction. Anyway, this is what we call the supervisory control. So if you compare the block diagram here with the autonomous vehicle, you see the mechatronic system maybe can be very, very complicated. This is only one vehicle. I think everyone in the class will know in the next 1 or 2 decades, the vehicle will talk to each other, the IoT. So it's not only the one vehicle, maybe thousands of vehicles, they are talking to each other. It's a network. That would make the mechatronic system more complicated. And we are going to, in our agriculture field, this is also one of a technology booming to use this kind of technology for agriculture, harvesting, or within many applications. Okay. So from now on, I'm going to introduce each element in this mechatronic system. So if you are familiar with that, I just review. If you're not, it's the first time you will have some basic concept what's going on in a mechatronic system. So first of all, I'm going to introduce you the sensor, the sensing technology. Here, the sensor may measure some physical properties like position, velocity, acceleration. The sensor can also measure some force, torque, pressure, temperature, moisture. The sensor also can be used to measure the chemical properties such as nutrition contents, ion concentration, blah, blah, blah. Many, depends on what kind of properties you are interested in. You can find a proper sensor or develop proper sensors for your application. Okay. So here I provide some basic sensor. For example, first of all, this is potentiometers. It's kind of a variable resistor. So this is resistor, but there's a wheel. So when the wheel is rotating, here, the resistance, the output resistance will change. And if you connect this to power supply, the output voltage will change. So the output voltage will relate to the angle of the shaft. Okay. So basically, a potentiometer consists of resistive elements. Okay. And there's a contact, sliding contact, which can move. Depends on to measure the linear or angle. This is for the angle displacement measurement. And this is the linear displacement. And that's for the linear resistance here. This is the resistor. And this is the contact. We call precious metal fiber here. Okay. So this is the shaft connected to your plant. So when you move, the resistance will change so that you know the position, the linear position, linear displacement. Okay. And as we see, we have to model in mathematics. This is one of the very important concepts. When you construct your mechatronic system, always think about, can I build a model for such a mechatronic system? Because with the mathematics, we can start to analyze the behavior of the system. As we mentioned in previous slide, this is very crucial for you to design your mechatronic system. You should be able to analyze that. So this is the sensor, potentiometers, right? And you connect the output voltage to your device. There's a load effect. If your device, we call the output impedance, is infinity, then the relationship between the voltage and the position is very simple. For example, here, this is the total, the power supply. We call the Vs. So we just calculate the proportion, the ratio of the output voltage to the power supply. We can know the position of the position, the displacement, right? Okay, this proportional. Okay. For example, if this is 50% of the voltage, then you know the position is in the middle place. Unfortunately, the load effect, the output impedance is not always, okay, it's not infinity. In reality, no. It's a finite resistance. So there's always has an error for your measurement in your model and the actual position. So you have to be aware that the error you measure from your sensor, so that you can, in your controller, you always think about it as an error, so you can correct the error. If your controller is very complicated, then you can deal with the error. This we call the source of error. So in your model, if you have you are aware that, and you have a model to model the source of error, then your system will be more accurate than others. That's very important. That's we call the analog sensor, because the output is an analog signal. It's a voltage. And as an analog sensor, it's fragile. It's very sensitive to the noise, the environment. In our environment, there are many interference. So in order to have a more stable sensor, this is a digital sensor that measure the same function as we just in the previous slide. They can measure the angular displacement, also the linear. Here is the angular. The encoder here is a digital output. Okay, and there are two types of encoder. What we call the incremental encoder. So the displacement, the angular displacement, we are related to the pulse, the number of the pulse. And typical resolution here we show here is 2,000 counts. So you just calculate how many pulses, and you know the angular displacement of the shaft. Another is called the absolute encoder. They will not give you the angular displacement. They give you angle, the absolute angle, okay, of the shaft related to the initial position. It's called the absolute. Okay. And this is the working principle of incremental encoder. So you look at in this encoder, there's a disk, and in the disk they make the slot. Okay, the slot you can make by yourself. You can make by yourself. For a primary school, the year 7, the high school, junior high school, they start doing that. Okay, using a very simple fire a disk in black color, and they can do that. So you make the slots. Okay, so for example, the 2,000 counts, we make 500 slots in a circle, in a term, and you make 2. So this is we call the channel A, and inside we have a channel B, and they have the LED. This is light source and a detector. So you can imagine that when you rotate, and when the light touch the slot, that will penetrate, and the detector will detect the light, so it goes up, right? But if in the middle there's no light, they will going down, right? And you have the channel A, you have channel B, and they put channel A and channel B with a 90-degree phase shift. So the slot will be slightly offset from the channel A, a bit, 1/4. Why? The purpose of that is that, you see, if you do that, you can see that would generate a very interesting things. Like this is 0, 1, this is 1, 1, 1, 0, 0, 0. So the resolution will increase 4 times. So only 500 slots, but you can generate 2,000 pulses. 2,000. You can measure the 2,000. I can say you can increase your resolution to 2,000 by coding. This is one purpose. The second purpose is that in your register, you just see, you can look at the sequence. If the sequence is 0, 1, 1, 1, 1, 0, and that means the shaft is moving clockwise. But if the signal you receive in your register is like this sequence, then that's anti-clockwise, right? So they just look at the sequence in this direction or in this direction. They can also measure the direction. So with channel A and channel B, you increase the resolution. You also provide the detection of the direction. It's the incremental encoder. It can make it very cheap if the accuracy is not so. And another one is called absolute encoder. That's different. It's more expensive. You need more LED and sensors to measure that. So, for example, this is 10. The resolution is 10. Then you have lots of slots, and they are designed very differently from the incremental encoder. So this is we call the gray code. Gray code. The gray code. So they just detect the gray code. They will know the shaft is in this area or this area. Okay. And by increasing the resolution, you will be able to measure a very small angle. Okay, let's go gray code. That's a very brief introduction of how to measure the angular or linear displacement. The other thing is to measure the angular velocity, called a gyroscope. Sorry, this is also can be used to measure the angle as well. Okay. So in the middle, there's a very high angular moment of inertia I, and also high speed angular velocity. So the angular momentum of this part will be very large. And according to the Newton's second law, if there's no any external force or torque, this angular momentum will remain the same, right? Related to we call the inertial frame. For example, universe, the inertial frame. So they equip this device, gyro, on the airplane. And this arrow will point to one the Earth without any changing, right? But the airplane will change the we call the pose of the airplane, right? They will, when they take off, the pitch angle goes up, going down, low. So they just attach this to the airplane, but because this is always point to the fixed direction, and the outer ring will change. So they measure the angle of the outer ring. They will know the posture of the airplane. This is the working principle of gyroscope. So there's a device That would, again, inside the gyro, they need to have a very good mechatronic system to maintain the constant speed of the angular speed, right? If there are some frictions, they have to compensate so that to make this gyroscope in more accurate way to measure the angle. Okay. Low PGO. In this case, that's mechanical gyro. In this case, we use more technology from MEMS. Okay, the MEMS. So here, if you have any angular velocity, they call anchor, they are going to change the vibration, the acceleration in these elements. So they measure their acceleration pattern. The frequency. They were able to measure the angular velocity in the middle. Okay, that's a working principle for this MEMS gyro, and they can make it very, very small. In more detail, you have to go to the reference to see what is going on. Okay, that's the basic idea. Okay, and we also can use the MEMS technology to measure the acceleration, called the accelerometer. They are using the basic idea that the second order mechanical system, you have the mass, you have the spring. So you measure the pattern, you will be able to measure the acceleration. Okay, so this is the basic idea. And this is the standard second order system. So you will be able to measure the external acceleration. Okay. And they can make it very small. So this is the accelerometer. And we also can use the magnetic field on Earth to measure the absolute orientation as well. Okay. And this is the mechanical. This is also, again, this is the MEMS technology to measure the angle. They're called compass. I think I don't need to talk about compass. When you go hiking, you have in the ancient time, you have the compass to know where you are, right? The nose, the direction of the nose. That's the idea of the compass. So in these days, they combine accelerometer, the rate gyro, and the magnetic meters together, provide a night output. They call the IMU. So at the same time, you can able to know the acceleration, the velocity, angular velocity, also the orientation relative to the Earth. This is just provide you a raw data, right? In this test, you need to process the measurement by your algorithms. We call it data fusion. Then you can output the actual position of the vehicle and also the orientation by your algorithm. Okay, right now, okay, this is MU. And we also have another sensor to measure the position of your objects. Here in Taiwan, we are using, we are using a system called GPS provided by the US. And this system developed originally for the military use, for the orbit missile. Okay. Okay. And nowadays, they are accessible for commercial applications. And in the system, there are 33 satellites at a height of about 20 kilometers every 12 hours. And so, because there are 33, so at the same time, probably your area is covered at least 4 satellites. So you can use these signals provided by 4 satellites and calculate where you are, the position. Of course, more satellites will improve the accuracy of the GPS. In Europe, you have right? You have another system. Do you know the name? It's I don't know Chinese. And Japanese has their own, and China, Russia. Every country, they prefer to have their own satellite system. So that's the GPS, the global position system. For the vehicle avoidance, this is a very cheap solution. The ultrasound sensor, very cheap, very effective. So in the ultrasound sensor, you can measure the object between the distance between your object and the obstacle. The working principle is that inside an ultrasound sensor, they have a piezo elements. Anyway, it's a piezo actuators. So it's a piezo. So you have a voltage applied to the piezo elements, then they will vibrate, right? Generate the mechanical wave. And at the same time, if there are some mechanical wave inside, they will also make these elements generate the voltage output. So it's 2 directions. You give the voltage to the elements, they can vibrate. There's some vibration, they can generate the voltage. Okay, so that's the working principle. It's probably, you know, this is invented by the husband of Curie, the Lady Curie, 居里夫人. It's a very brilliant physics. Okay, so we use this working principle. We can detect, for example, we can detect you send the mechanical wave and you wait, and then you can hear or you listen to the echo, and depends on the time duration, you can calculate the distance. Okay, but you have to be aware that the ultrasound, because it's a wave, there's a direction. Okay, the wave has a direction. Okay, direction. So that's why in the rail of a vehicle, you need to put more ultrasound sensors. If you put just one sensor here, you won't be able to detect this area, the obstacle in this area. Okay, this is ultrasound. So here at this time, you send the voltage to the piezoelectric elements. So this is the driving signals, right? So they generate a mechanical wave, send it out, and you wait until the echo, and you measure the time. We call the falling edge, the falling edge. So you calculate the time duration, and this is the time duration t, and you multiply by the speed of the sound and divide it by 2, because you go and you back. So divide the 2, and you are able to measure the distance between the obstacle and your objects. Okay. But you also have to be aware the speed of the sound will depend on the medium. This is so. For example, if you use your ultrasound for human body, you have to know the speed of the sound in your tissue. It's different from in the air, and that will be able to generate the more accurate output. Sound right? But you also have to know when you use ultrasound to detect the distance, you have to be very aware the artifact of the ultrasound. For example, if the object is located not in the direction of your mechanical wave, and it will create, we call the virtual object. Here, there's a wall. This is the wall with a very smooth surface. So the mechanical wave will like reflect a little bit angle, incident angle, touch the object, reflect again. But because you are not aware, you will think the object is in your direction. And if you use the this kind of distance to move your vehicle will collide with the wall, right? This is called the artifact. In order to solve the problem, you need more sensors. That's why we usually use many ultrasound sensors. We call the ultrasound array. Okay, ultrasound array. Ultrasound is relatively cheap, so you can do that. And to measure the distance, you can use the ultrasound. You can use another one is called radar. Especially in these days for defense. So this airplane, you have the radar. Radar is a radiant. They are sending out the radiant frequency, RF signals. You know, so the radar is moving, is rotating, so it's detect everywhere. You know, they're sending the signal out, and then they are also waiting for the reflected signals, and then because in the air they always have lots of reflected signals, RF signals. You are here. If you have a sensor, you always have RF signals into your sensor. So they have algorithms here. What they are doing is that because you are setting your special, we call a modulator. Where is it? Here. This is they call, for example, I have a radar here. And then I don't want our enemy to know I have a radar. So, but from the enemy point of view, they are always try to figure out, is the radar detecting me? Try to hide myself, right? So you have to modulate your signal, sending out like a noise. So nobody knows, is it a noise or is a signal sending from the radar? But you know, this is the code. So you listen to the echo, compare the pattern with your signal sending out. If they are very similar, they must be your the signal reflected, right? If they are not very similar, they are noise. So they are using, we call the correlation maximization. They will calculate the time duration and times the speed of the light. And then we will be able to calculate the distance. That's called radar. And the advantage of using radar is that for ultrasound, you cannot send because it's a mechanical wave. And if the object is very far from you, the energy would degenerate a lot. But for these RF signals in ice air, they can penetrate until 1 kilometer. So it's a long distance sensor, very effective. Okay, this is why they are using data. In maybe 10 years ago, for the auto parking, originally they were using ultrasound and IR sensors. It's not reliable. They are implemented in the BMW. Finally, they found radar is more reliable because when you park your car in raining, and ultrasound or IR or any, they are not reliable. But radar is very reliable. They can penetrate and give you a very stable signal. So in these days, for autonomous vehicle, they still use the radar technology for measurement. Okay. So they equip the radar, and then they can measure the distance from your vehicle with your obstacle, right? In very robust way, robust, very stable. Okay. Especially in a bad environment conditions such as rain or fog, because you are going to implement your sensor in the vehicle, which maybe if you move in a high speed, it's a very dangerous situation. You need to have a very stable measurement. Okay, so they use the radar for adaptive cruise control, car following or something. This is the sensor, probably frequently used by students for practice the autonomous car, the IR sensor, very cheap. So this is LED. Okay, this is a light source. So they emit infrared. And then if this is the object, the reflection, absorption, but they also have a reflected infrared back to your sensing equipment here. So you measure the optical power, right? And then there's a relationship between the power you detected by the sensor here, and you can calculate the distance. The distance is inverse square proportional to the intensity, okay, of the infrared. And because the sensor, they receive okay, so the optical power from the environment, they may be also again contaminated by environment lights, right? So usually in the sensor, they have a maturation as well. They probably have a frequency like 100 hertz in order to, because for our lights, 60 hertz. So if they sending out the IR in 100 hertz, you will be able to demodulate, separate the light source. Is it from your emitter or the ambient lights? So that's also have a maturation technology here. And you look at the IR sensor, there are two. Why? Probably you say one is enough. If you have more emitter, LED, in your IR, you can actually control your direction of IR light to any direction by we call beam forming, okay, using the sequence, time sequence. So if you fire your LED from the left to right, so left will move in front of right, right? So the wavefront will in this direction. So that's, you can control the direction of your IR light to this direction or this direction. It's called beamforming. Right? So that's the working principle for IR. Very cheap sensor. So if when you are, this is usually used for light tracking. But in these days, students more like using the vision sensor. But it's very effective for light tracking. And if you are interested in more accurate position, you can also use, we call the position sensitive detector. They are using the same working principle as IR sensing, but in more complicated way, more good resolution. Okay, and the working principle is the same, and they make it linear by calibration techniques, whatever. But they are also using what they call triangulation technology. So you know the reflected light, the position, reflected angle here, and they will calculate by this equation. They will know the distance of your objects. Triangulation methods to do that. So that's we call PSD. Okay, that's a case. I'm going to introduce a lot of sensors because this is very important for you to make a electronic system. And this is the laser rangefinder. It's only one direction. So is this the laser? They're sending out the laser, the lights, and they detect the reflected lights, and they calculate the phase shift. You cannot measure the time flight because this is the speed of light very, very fast. You measure that, it's impossible. So one thing you can measure is the phase, because laser is the magnetic signals that have a frequency. So you measure the phase, you will be able to calculate the distance. That's the one direction. And in these days, there are two directions. They're rotating the laser rangefinder, so they can know in 360 degree to measure the environment that create the point cloud. And if they make it up and down, they can generate the 3D point cloud of your environment. That's called a LiDAR. And they use the LiDAR, for the vehicle navigation. So they generate the map. They can know this the human, the car, the environments. They give you the data of the environments. And if they have the model for the point cloud, they can mention with the point cloud, they can recognize the objects. This is a pedestrian, this is a bicycle, or the car, and they make the decision, the pace, the desired pace is going to turn a little bit right to avoid the things, or this is the car I have to follow. This is all based on this data cloud and the object recognition. And this is the last. One of the most also very important sensors, the vision, stereo vision. So they use two cameras to take the images. If you have the model, you will be able to calculate the object here, the location of the object from these two images based on your model. I'm not going to explain very detailed how it works, but I just point out when you use stereo vision, you have to know the limitation of the stereo vision. It's called disparity. For example, if you have two eyes, right? Left, right. If you close one of your eyes and you go to an area, you will be able to have a very accurate estimation of the depth of the object, right? But you have two eyes. Why? You have two eyes, so the left-hand side, the image in the left-hand side and the right-hand side, they are not completely the same. They have a little bit difference. We call it disparity. We use this disparity and have a model so that we can calculate the depth of the objects. So that's the working principle. But if we look at the stereo vision system, And well, anyway, this is very, very complicated. We simplify these two matrices, nonlinear matrices. We can see from these equations, they are inverse proportional to each other. We will calculate the sensitivity of these equations. We will know the sensitivity of the depths is square, inverse of depth square, right? What does that mean? Means that if the object is far from you, the disparity will decrease dramatically. That means you won't be able to make a very good estimate of the distance, right? For example, if the object is 100 meters away from you, and the other object is 101 meters from you, you won't be able to make a very good estimate because this is the nature of the stereo vision. So that's why sometimes they put two cameras away from each other, right? That makes this disparity more significant, but you won't be, right? And this is also applied to, they call radar array. I don't know. They detect the signal from the space, the universe. They put it out. And if this sensor can be very, very long distance from each other, they make the resolution much better. Okay. This is a physical property of that. Okay. So you know that. So in order to do that, you have to analyze your stereo vision system to think about your disparity and make your model in the area you are really interested in, right? So that you can make your stereo vision system more accurate. That's one thing you have to bear in mind when you are using a stereo vision for the distance measurement. Okay. Oh, we are running out of time. So originally, I was planning to have a short break, but I think I had better continue my presentation. So let's give you a lot of introduction, many different sensors. I think it's quite important when you are making a mechatronic system for agricultural application. And then we look at the actuators. I'm going to make it as short. So here, there are 4 types of motors, probably quite frequently used in industry. One is a DC motor, DC brush. There's a brush here, this DC brush motor. And also one of the very important, we call the brushless DC motor, especially for the vehicle, electric car, and stepping motor. Okay. And in industry, we need a large torque and energy efficiency. So, and also because their power is mostly in AC. So it's AC motor. Okay, so 4 types of motors. We are going to give you a brief idea. And again, in order to make use of the motor properly, efficiently, probably you need to have a mathematical model to describe, analyze the behavior of the motor so that you can control the motor in a better way. So this is the model, mathematical model to describe the behavior of the motor. The motor, you have a magnetic field, you have electrical field, the interaction between the magnetic field and the electric field, then you generate the torque, the mechanical torque, right? We are using this property to construct our motor, right? So eventually, as a mechatronic system, mechatronic engineer, we are aware that the torque generated by the motor is proportional to the current we send into the motor. Okay, and the constant we call the motor constant, the torque constant, right? Very important. When you buy a motor, you always have to look at the motor constant. The larger, the better, right? So you can buy a very small motor, but it can generate very large torque because the current constant is very, very big. That's because they have used a very, very strong magnet in their motors, right? Okay. That's one thing. The second thing you have to know, because you have to send a current to the motor, right? So there's an electric load there, the current here. The current cannot be generated as large as you want because it's covered by these equations. They have a resistance for the wiring. They also, when you move, they have the back EMF. And because this is the current generated magnetic field, they will have a inductor effect as well. So it's covered by this equation. And at the same time, because they generate the torque on the shaft, they also covered by the mechanical equations here. So you combine these two again by the current, as we say, the torque constant here. You can connect the mechanical to the electrical by this equation. And using this equation, you can have a block diagram of a DC motor here. So you have this small block diagram that gives you a more clear that what kind of parameter is going to influence the performance of your motor. Very important, very good block diagram. You have a motor constant. You have a KB here. Back EMF is also another very important factors. And then the armature resistance, inductance, and also have the moment inertia of your shaft and the bearing friction. These parameters will strongly influence the dynamics of your motor, as I mentioned. But you can use in control, right, to design the dynamics of your motor. As I mentioned that. So in these days, they have a controller we call driver. For the motor, we call servo motor. The purpose of the servo motor is to design the dynamics of the motor to meet the requirement by the users, right? So this is only the motor. If you combine with a sensor, like an encoder we just mentioned, the computer, then, and also the power electronics, then you can make your motor, DC motor, as a servo motor. And then you can improve the response time, the accuracy, and also the overshoot. So that's the basic. And sorry, because there are many, let's still have a brushless DC motor, stepping motor, AC motors. But because the time limits, I only I give you some concept about the DC motors. But we also have another actuators, which is now motors, like electromagnetic valve, hydraulic, pneumatic, many different, and the piezoelectric, many different actuators. So you bear in mind, there are many actuators. Depends on your needs. You have to choose the right actuators for your system, your objects. So sensor actuators. What about the controller? The controller. Here, I just give you a very short introduction of the controller. First one is called long model based. Very easy. On off. So you have a switch, relay, and then you measure. If the speed is higher than you expected, you slow down. It cross your engine, then you slow down, right? Or actuate the brake, slow down. If the speed is lower than you expected, you open the throat, they will increase the speed, right? On off. So in your control unit, it depends on the error. You switch on or switch off your actuators. That's called on-off. Right? But this will have some problem. For example, for the students, they are making the goal from move or the vehicle from A to B. So they calculate, because the distance is positive. So they move the vehicle towards to the goal. And when they reach the goal, 2 over, they turn it back, right? And then so if I using on-off control, you can see the vehicle is like moving back and moving forward and backwards. You know, it's like acceleration. On-off control will produce very significant acceleration when you reach the goal, in the area of the goal. In order to reduce the effect of acceleration, that you can, in your computer, you can write a code, write a program with a dead zone. Like when you reach this area, turn the power off. So the car will like, and then stop in the nearby of the goal. So they will reduce the acceleration, but the accuracy is not good enough. Because in the dead zone is larger, the acceleration will decrease, but the accuracy will also degraded. That's the thing. And there are also another on-off control, but in more sophisticated way. If the load is not it's a little bit up here or down here, then you probably need to make your program more complicated, depending on the direction. Hysteresis control. All these are categorized by we call the on-off control. You don't need to know any model of your control object, the plant. Depends on the current sensing information you decided the output. I think it's not good enough. The performance is not good enough. So another is using we call the PID. You can see the control signal. It's continuous. It's continuous signals. It's more sophisticated, based on the error to determine the output. So error is larger, then the control signal is larger. So you can see the car, when away from your goal, is moving faster, but then reach the goal, they slow down the speed. Finally, they will stop at the goal. That's the idea of a proportional feedback control, right? But unfortunately, many systems, if you use only proportional control, they will accelerate again. But eventually, they will slow down. As we see, you use proportional control, you can improve the response time, right? Because if you are using on-off, you're moving constant speed, right? But if you are using proportional control, because when they are very far from each other, they are moving very fast and then slow down, right? So ideally, that will improve the response time, make your system more quickly. But unfortunately, some system will make it a little bit overshoot. Because if you increase the gain, it's going to be overshoot. That's another thing we call derivative control. They will give you some damping, some prediction that you are going to reach your goal. Please slow down. If you are not slowed down enough, they will give you some resistance force, try to stop your car. That's the purpose of that. So this is going to give you the system more damping, improve the overshoot. This is also implemented in, as I mentioned, for a luxury car that improve the acceleration after bumping using this kind of control algorithms. And we also have another we call integrator control. If the error, if the final error, no matter you are using P proportional derivative, error is still there. Then you integrate the error by time. So when time is over, is going, the action will be larger, right? And finally, the output will be able to correct the error. So the integration control will improve the accuracy of your system. So in short, proportional improve the response time of your system. Derivative improve your overshoot of your system. Integrator improve the accuracy of your system. So because the PID is so straightforward for their physical meaning, that's why the PID is very popular for industrial application. Without knowing any model of your system. Very good. So why we need a model-based controller? Why we need to learn a lot of theory to build a model, to do the controller design? Why? We can just use PID, just enough. I just give you an example. In 10 minutes, this is the autonomous vehicle in Archer vehicle developed by Carnegie Mellon University for the localization and control from this journal, Computer Electronics in Agriculture. So this is the autonomous vehicle in Orchard. Sorry. Here. So you can see here, this is the LiDAR, right? As we mentioned here, there's LiDAR. So in this paper, they use LiDAR for the measure the distance, localization and distance from this landmark. Okay. They have many applications. They can do harvesting, programming, thinking, lot of many applications. Right. So they need a model. What kind of model? They are built the kinematic model for the autonomous vehicle. They are not going to control the dynamics of the car. They just control the kinematics of the car. So it's not very complicated, but it would give, we will see the result. They will improve the performance of the overall performance. So this is the car. I think it's this is the real wheel drive, but there's steering wheel here. So this is the steering angle, all right? And they model this into a bicycle model. So the real wheel will provide the speed, and the steering wheel provide the steering angle. Okay, so there's two parameters. Okay, and this is the speed of the vehicle. So first of all, you have to find physical variables to describe the behavior of the system, right? So this is how they use mathematics to describe the behavior of the system. So finally, they derive the equations for this kinematics for the vehicle. Okay, I'm not going to explain the equations. This is not the purpose right now. Okay, so you have x, y. This is the Cartesian coordinate of your vehicle to describe the location of your vehicle, right? And this is the omega. It's the speed of the real wheel, right? And this is related to the steering, the steering wheel, right? The phi. So there are some relationship. And this is the v. V is the speed of the vehicle, the forward speed. And they also have another parameters, is axis distance, something like that. Okay. So with this model, if your desired path, as I say, you are doing the path planning, right? You need your vehicle to move along this curve. You need that. This is the path planning. Then how your controller have to do anything for that purpose, right? Depends on the measurement. Okay, the sensing, the LiDAR, the measurement. Okay, so this is the equation they do it, but I think it's more complicated. Yeah, you must know that you need omega, you need the right wheel and left wheel. The solar also have another governing equations, right? So depends on the arrow, you can based on this model and calculate the speed for your right, your left wheel, and then you can do many things. Oh, this is not right, left. This is their control variable is the omega and the phi. Okay. So you control these two variables. Okay. So this is we call the model-based controller because you have the model already here. You calculate the speed, the railway speed, and the steering angle, right? This is the control signals, right? And based on the sensing, so you have a sensor that here, the laser rangefinder, and also you generate the pace, right? And this is the model you calculate, and then you can do that. Almost, right? And that's the schematic. So we will see the video. So they are doing this. Okay, based on the model. So they have a lot of different schemes how to turn the vehicle in opposite direction. They also do that. Path planning. This is what we call the path planning. This is what we call the trajectory planning. This is the pace, and then in each point, what kind of speed is going to be. Okay, and this is the localization, how they calculate the position. All right, this is performance. So this is the model-based controller. You can see if you are not using the model is more concentrated on the arrow, on the zero, on the center. That means the average arrow for the model-based controller is much better than without the model. Okay. The blue line that indicate that your vehicle will follow your planned path on the right track to do the job, something like that. We see. Let me show you the video, and then we can. That will be today's video. Okay. So. Morphing. Okay, sorry. This is even more complicated because there's a trailer. This is not easy, right? I think my student will know because there's no marker at all in the turning area. When they enter into the row, they have a sensor input. That's fine. You can collect your post, but in the turning area, how you can do that? That's the challenge. This is, they are taking some images. We just speed up and so the vehicle is moving autonomous and cooperative with the workers. So they will know how to move. You know, there's no people here driving the car, but they know when to move the car and to stop the car. Even the human being is stand on the vehicle, and they will know, how to cooperate with the human being. Cannot move too fast. Okay. Hopefully that's the thing. Yeah, that's the vehicle developed by the CMU. I just show you the last video. I think it's last year. It's a famous the Blue River acquired by Deere Johnson. So that's the commercial by the Blue River. This is also one of the. Okay.
We're looking for other ways to combat the weeds and still have cost savings on top of everything.
We saw an opportunity to take cameras, computers, and artificial intelligence to allow ag machines to see every plant in the field. We thought that we could give farmers the ultimate flexible tool to treat their field and manage their field in whatever way they wanted by having the knowledge of every plant and its situation and an ability to spray very precisely, whether it be herbicide only to the weeds or fertilizer or fungicide directly on each plant that needed it.
Each field they go to has a different set of conditions, and they need to be able to adjust and correctly set that machine's performance for the field. One knob could be the protection of the cotton plant and how big of a buffer, a safe zone that we provide the plant so that when we apply selective materials or not selective materials that we have the appropriate buffer. Another dial is how aggressive do you want to be at going after anything that looks like a weed. There's also some opportunities to inform the grower of how many weeds the system's seen, even what kinds of weeds exist in the field, that they can start to tailor their herbicide programs towards those weeds.
The cameras and computers on the See and Spray machine are using deep learning algorithms that are similar to what's used in facial recognition. The first time we saw a pigweed, the machine didn't know what kind of plant it was, but we taught it by giving it tens of thousands of examples of that pigweed, and now it's an expert in pigweed. We save up to 90% of the amount of herbicide that you would spray if you were spraying the entire field.
The weeds have become a little bit more of a pest than what they were originally. They've become resistant to a lot of herbicide that we've been using on.
With the rig, we have other options open to us. We can spray different chemicals that we're not able to spray before. We can take one man and put him on a tractor, and we can do the work of 8 to 10 people.
We're seeing people are into the use of this technology. Essentially, anything that may be cost prohibitive or more difficult to do when you're spraying on a broadcast basis, much more beneficial if we're spraying on a very precise basis.
So, because of the time, maybe. Okay, so that's. Similar system. Professor Shui-Ming Chen also have a system for this Blue River, what you just see in the Blue River, yeah, for the vegetable as well. So that's all about today's presentation. Any questions? It's a little bit late. If not, so that's conclude my today's presentation. Thank you.
This one. Okay. Next week is last week. We're going to have our own class together, and I'm going to last century and this century, and so you'll see what we have achieved, what kind of achievement we have done before, and what kind of challenge we're going to face in this century. And after that, fifth week, 2 weeks from now, and then we're going to have a joint class with the two universities in Japan, Kyoto University and University of Tsukuba. And then we from that week on, we are going to be really busy about the screens and everything, and also discussions. And so it's great. We're looking forward to it, and I'll see you next week for the engineering roles in this century and next century. All right, thank you.